All right, so today will be our last lecture for deep learning course, CPG 586. And I think I already sent you the announcement that the final exam will be next Saturday, right? Which is, I think, 14th, right? Same 10 a.m. Okay, and this will be not in Tech 116, but it will be in Dana Hall. So Dana 107. And I will send you a reminder, right? And the material will be after the midterm. So whatever we covered after the midterm exam, that's what we will ask on the exam, right? So again, simple multiple choice questions. If you've been following the lectures, it should be pretty straightforward, right? We have already covered, or I have assigned you assignment 7 and 8 that hopefully you guys are working on, assignment 7, 8. And I'll give you one last assignment, assignment 9 today, so that whatever material we had in mind to cover for the course, you guys are knowledgeable about all the foundational concepts as well as programming related to deep learning, right? Okay, so assignment number 7, if you recall, we are looking at deep convolutional neural networks. Okay, and you are experimenting with a ResNet architecture. So we discussed that in ResNets, if we have a CNN layer. Okay, and we create many CNN layers in a deep network, right? They keep learning important features. They all do important transformation about the input. So if we have some input image that we fed over here, right? So suppose this is X. As it goes through many, many layers, okay, it's learning the important aspects of the image as we apply different convolutions. Within each layer, we have multiple convolutions going in parallel. Then we combine the result of these, as you guys saw last week in the architecture of the CNN. And at the very end, what happens is whatever we are left with, we flatten it into a vector, okay? So this output, after passing through all the CNN layers, this is what we call our latent representation of the input. Okay, so for example, okay, let's say our input image is 100 by 100 pixels, right? So you can think of it this way: in a 10,000 dimensional space, whatever that space is, right? This image is somewhere one point in it in this 10,000 dimensional space. Okay, so as we are going through the different convolutions and different layers, we are transforming this into a relatively smaller dimension. Let's call it a latent dimension. Okay, for example, at the very end, let's say we are left with 120 as an example, 120 numbers. So think of it as if after we went through all of this, there's a 120 by 1 vector, the latent representation. So essentially what we did is we started with the 10,000 dimensional data. Through these convolutions and different layers, we are translating it to some other point in, for example, a 120 dimensional space. Okay, main point I'm trying to make is all of our deep learning these days operates in a vector space where we operate on vectors, we transform vectors. Then once we have transformed them to a particular dimension such that there's high distinction between one type of category, one type of image, or to another type of image, then in this latent dimension, we'll apply a classifier. Okay, and whatever number of categories we want to categorize in, the classifier will translate now or create, I shouldn't say translate, it should now create decision boundaries over here between the different classes. So it creates decision boundaries. Between different classes. Okay, so if we have one class over here, for example, one class over here, okay, another class over here. Okay, so however many classes we have, for our training data, it will create these boundaries so that if an unknown data is given to us, for example, if it belongs to X category, it can easily recognize that it belongs to this category, right? So this is the general idea of creating deep networks. Start out, transform the higher dimensional data into some latent space so that things are easy to distinguish. In what we are doing through all of these convolutions is we are learning the features. So these convolutions are basically doing feature learning before we do the classification, right? Okay, so how do we set all of these deep networks? So last couple of lectures, we talked about that you will be using the PyTorch library. So in PyTorch library now, just to quickly refresh your memory, we need training data. Okay, training data usually for classification problems comes into set of inputs and the corresponding outputs. So this is the target or the expected output. And this is the input data that we want to categorize and why is the category for this, right? So we'll be given a lot of X's and the corresponding category or the Y that it belongs to. So if you recall, the concept in PyTorch was create a data set. Okay, data set will contain all X's if we have enough memory in our computer. Okay, and the corresponding Y's. So all X's and the Y's. Okay, we will store this, right? We will write one simple function over here, get item. If somebody calls this get item, it will return one data, meaning one X and the corresponding Y to whoever calls this, right? So typically with the data set, what we do is we create a data loader. And the data loader decides on the batch size. Usually we use batch size of 16 or 32 or 64 with images. Okay, which means our data loader will keep calling the data set, keep calling the get item to obtain one item. And once it has obtained, for example, 32, if the batch size is 32, now you can see the 32 X's and the corresponding Y's can be given to our training code as an example. Okay, if we are testing, we will obtain another set of, we'll create one more data set. So typically what we do is we'll create a trained data set. Then we will create, for example, a smaller test data set, which the model does not see until it is trained. And then once it's trained, again, we will call the get item over here to test how good our model is, right? Okay, when we set up the data loader for the training purposes, meaning the train data loader, okay, we don't want to obtain all the X's and Y's in sequence, okay? So we basically shuffle the data so that shuffle data in data set so that every time it uh, uh, to our training code, it provides a different type of data. This way our training is more effective and the network trains a lot better, right? But once it's completely trained, then during testing, we will create a test data loader. And now as we call the get item, okay, now the batch size is not important. If our test data set is small, we can obtain all the data in one batch. Or if it is too large, you can still create a larger batch size. So now we will not shuffle the data because it doesn't matter whether the data we are feeding for testing purposes is randomly selected or it's in sequence. So here, the test data set does not do any shuffling of the data, right? Okay, so now once the data set has been prepared, okay, so the data set has been prepared for the training. Test data set has been prepared. You will associate the train data loader and the test data loader with the corresponding data set. You will decide the batch size and the shuffle, whether shuffling is needed or not, right? So this typically I write it in the utils file. So I will write some function, for example, get loaders, and then write the code to, after the data set has been created, to create a data loader, associate with the data set, and keep obtaining and at the very end, we return the train data loader and the test loader so that our training code can utilize these and train our network, right? So then, if you recall, the next goal was whatever deep network we are creating, whether it's two-layer CNN or ResNet with dozens of layers, it doesn't matter. So we will create a class called MyNetwork. Okay, and the base class will be torch.nn.module. Okay, then in the definite, we will describe the building blocks, whatever parts we need to build our network, whether it's a CNN layer, whether it's a linear layer, whatever activation we need. So we'll define the building blocks. And then in the forward function, we will take the input X and we will pass it through our network. So here we will keep, feeding it to our model, whatever the building blocks are. We'll feed X to them, they will produce some output, then we'll pass it to the next layer, whatever this is. It will produce some output, then to the next layer, whatever this is. And at the very end, we'll return the output. Okay. And after we have created the deep network, then in our main file, we simply have a training loop. And we have a test loop. So that after it's trained, we can test it, right? So after you've seen some examples of, especially like carefully examine assignment number 7, you will see, this is what we are doing. So let me quickly take you to assignment number 7. So Okay, we are doing the Cypher10 classification. In the first part, we create a very simple CNN. In the second part, we create a deeper ResNet type of architecture. Okay, okay, like I said, I start out with utils file, as I mentioned, and uh, we basically, as you can see, in this case, rather than calling it get loaders, I called it prepare data. And as you can see, it will read the Cypher10 data. It will normalize it between -1 to 1 because images are usually between 0 to 255. So if we use our transform with the 0.5, we went over it last time, then it will end up transforming all the pixels between -1 and 1. And at the very end, this is what's important. We want the train loader and the test loader to be returned by this function so that our training loop can use the train loader, our testing code can use the test loader, right? And if you see when we set up the train loader, what did we do? Shuffle equal to true, right? And we'll pick some batch size. The caller will decide what the batch size is, for example, 64 as an example. So that's every time train loader is invoked, now it will return 64 randomly selected images from the Cypher10 dataset. Okay, if you take a look at the test loader, as we create any of the loaders, the first thing we do is we tie them to a data set. CTrain DS is our first data set, which has all the training data stored in it, right? Cypher10 is a standard data set, so we are able to just call the Cypher10 object from the torchvision.datasets. But if it is our own images, then like I said, we'll read it from the directory where the images are stored and further go and put it as array of tensors or multidimensional tensors and store them in the data set, right? So same way for the test loader, we tie it to the, oops, do I have a mistake over here? Yeah, that should not be, okay, I have a mistake over here. So when you guys are doing the assignment, you guys can see this should be test DS. Okay. So I'll try to correct it, but I think when I copied and pasted, I forgot to change it. But the shuffling is false in the test loader, right? Okay, and then we can view the images and so on, right? Let's quickly take a look at the CNN model, and I think we went through it in the import torch. So base class is torch.nn.module. So this is our network that we are creating, right? Okay, from a final exam point of view, I'll be giving you some networks like this. And your goal will be to be able to understand it easily. For example, if I don't give you this size over here in the fully connected layer, because remember, as we go through different convolutions, so to give you an example, let's say you are given a 64 by 64 image. Okay, and let's say you apply, in the first layer, you apply, let's say, a 5 by 5 convolution. Okay, and you apply, let's say, 6 of these. So 6 feature maps, meaning 6 different convolutions, each is 5 by 5, right? So as you can see, how many things will it produce? 6, right? And what will be the size of each of these? So remember, it goes 64 minus 5 plus 1, so it will be 60 by 60, okay? Then if we do average pooling, okay, then what will happen? This will get reduced to 30 by 30 because it cuts the image by half. right? Okay, so anyway, 30 by 30 is how much? 900, right? Okay, so if I said, okay, we are passing it to a classifier, suppose just a one layer CNN, after, so 6 feature maps, then average pooling. So then I linearize it. So if I ask you what is the dimensionality of the latent space, so what will be the answer in case? It will be 900 times 6, which is 5,400, right? So if I'm creating a 2-layer classifier, remember each column of neurons, we create it as torch dot nn dot linear. So when we define a linear network, we indicate how many neurons there are. And what is the size of the input? So size of the input in this example is what? 5,400. And if I was using, let's say, 200 neurons over here, then this is how I will describe it, right? Okay, and suppose this is a 20 class problem. So on the final exam, if I ask you, can you tell me how the second layer over here, the last layer over here, will be declared in PyTorch, okay? So because it's a 20 class problem, output will be 20. What will be the input? So it will be torch.nn.linear. Input will be 200 because we said we are using 200 neurons, and then 20 is the output, right? So like I said, when you go through assignment number 7, it's not important whether it's running or not. I would like you to understand, what is it doing, and be able to, if we wanted to create our own networks, to be able to set it up and be able to run it, right? So anyway, this is the building blocks. And how did we decide the inputs and the outputs? As you can see, the first layer has 128 neurons, second layer has 64 neurons. Because it's a 10 class problem, the very last linear layer has 64 inputs because previous layer had 64 outputs and 10, right? When we set up a convolution, you should be very clear what is it doing. Okay, this is the number of channels that we are receiving. If it's a color image, it will start out with 3 channels. If it's a black and white image, it will start out with 1 channel, right? And what is 6? 6 is the number of feature maps, meaning how many convolutions are we doing in parallel? And what is 5 over here? That's the size of the convolution. So to give you one more example from final exam point of view, let's say we declared the con1. So self dot con1. Okay, and okay, so you'll see this will be torch.nn.conv2d because we are doing a 2-dimensional convolution. So this will be torch.nn.conv2d, right? And so now there are 3 things we have to specify over here. Okay, so let's pick the example. Let's say input image is 3 by 64 by 64. Okay, so 3 is the number of channels. Remember, red is 1 channel, green is another channel, blue is another channel. So which means I'm assuming in this example that this is a color image, right? And what's the size of the image? 64 by 64. So if this image will be passed to the first convolution layer, what should be the first number over here? 3. Okay, because it's a color image, right? Okay, how many feature maps and how many, what is the kernel size? So this is the number of feature maps. This is the number, this is the kernel size, let's say K by K. Okay, so let's say we decide to use 5 feature maps, and let's say we decide to use 7 kernel size. Okay, so what does that mean? That means once we apply this convolution to this, there will be 5 of these produced by the Con1, correct? And what will be the size of each of these? 64 minus 7 plus 1, right? So this will be 58 by 58, right? Sorry, is it 58 or 56? 7, yeah, 58, right? Okay, so 58, 58. Okay, suppose now I wanted to pass it through one more convolution layer, and in our definite, we created self dot conv2 equal to torch dot nn dot conv2d. Okay, and suppose, so now the question is, what will be the first number over here? Okay, see, previous layer produced 5 outputs, right? So think of as if these are the channels now. Just like in the very beginning, the color RGB acts as 3 channels. When this goes to the next layer, this is the number of channels. Okay, so the first number has to be 5. It cannot be anything else. Okay, now let's say we decide to apply 4 convolutions. Okay, and then let's pick the kernel size to be 9. So now what will happen over here? So that means each 58 by 58, what type of convolution we are doing? So what will be the resulting image then? 50 by 50. And how many images will we get? 4. Okay. If I further wanted to apply a third convolution, what will be the first number over here? Has to be 4. Okay. So anyway, study the code, experiment with it as you are doing the assignment. So let me go back to, okay. So anyway, at the very end, like I said, you'll see as many outputs as the number of classes, and typically we'll apply a softmax at the very end. So this is how we create the network. It doesn't matter whether we are putting 5 layers or 100 layers. The code is not too difficult to understand. And of course, if pooling is involved, every time we apply pooling, it will keep cutting the size smaller and smaller, right? By half, typically. Okay, then our main program, as you will see, it's pretty standard. It will go into a training loop. So we will create our network over here, and we will call our function to obtain the data loader. And in this case, okay. Anyway, so then this is our training loop. For epoch and range num epochs, enumerate train loader, and we just keep going and obtain the data. Once we call net and feed the data. See, inputs data came from the data loader, okay? Or the train loader in this case. I will increment every time we obtain the batch of data. So for example, let's say our batch size is 64. So, okay. So once we write this code for data in enumerate train loader. Okay. Okay, so let's say we have 64,000 images in our training data set. Okay, and let's pretend our batch size is 32. Okay, so my question is, if on the final exam I ask, how many times this loop will go through? See, I is the number of times it will go through. Okay, so remember, every time we are obtaining 32, right? So as you can see, this loop will go through 2,000 times before it runs out of all the images. Because remember, what do we do? We shuffle these. So after all the 64,000 have been shuffled, randomly shuffled, then we say, okay, keep giving us 32, then 32, then 32. So how many sets we will get out of our training data set? 2,000 over here until we run out, right? And typically, like I said, we further run it for many epochs so that each time it will shuffle, it will go through the data and train it, okay? So that is the philosophy of setting up deep networks and setting up the training. And of course, we have to tie it to a loss. So on the exam, I will also ask you about a couple of things over here. This was our network that we created. Once we pass net of inputs, which function does it call in our network? See if I go to our network. This is the net that we created. When we say, if we call that object net equal to CNN model, then if we say net and within parentheses, we give it some input, that's the input we are feeding it. So it implicitly calls the forward function. So we don't say call forward, we simply say net, and whatever network object we have created, we just give it the input, and it will end up now going through and calling and flowing through our forward code, right? Okay, so anyway, assignment 7 will give you an idea, like I said, how do we train and test the convolutional networks, okay? So even though the first part of the assignment is simply a 2-layer network, then we go and create a bigger network. ResNet basically gives us skip connections, and you will test it and see that this gives a lot better accuracy as compared to our simple 2-layer CNN that we create in the first part of assignment number 7, right? Okay, from a test point of view, let me see, there was one more thing I wanted you to, so if we go back to the training loop. Okay, as we discussed, PyTorch has automatic autograd component in it, which can automatically compute the gradients, meaning the derivatives and so on. So whenever we create a loss function and we say loss.backward, right? At that time, it will compute the gradients and store them. And then once we say optimizer.step, then it will update the weights and biases. Okay, so loss.backward. So once you create a loss function, and if you say loss.backward, okay, so this will compute partial L over partial W's, partial L over partial K's, the convolution kernels, partial L over partial B's. So all the derivatives are computed automatically by this one line of code. Okay, so once you have described an optimizer and created the optimizer, and once we create the optimizer, we tie it to the weights and biases of the network. And if we say optimizer.step, what will it do? It will take all the W's equal to W minus lambda partial L over partial W, all the K's, all the B's. So it will update So this updates the weights and the biases and the kernels. Okay. So these two on the exam, if I ask you what is loss.backward doing, and I give you a few choices, you know it's computing the gradients, right? Optimizer.step, what is it doing? It's updating the weights and biases, right? Okay, so assignment 7 now will give you very good idea of setting up deep convolutional networks. And generally, what is the philosophy of PyTorch in terms of data sets, data loaders, writing the training loop, test loop, setting up convolutions, linear networks, and so on. Okay, now let's come to assignment number 8. Okay, so now that we are feeling fairly comfortable with setting up deep networks, okay, and training and testing them. Okay, so the question is that all there is to deep learning? Okay, what's next, right? So now we talked about it briefly, but I will uh, emphasize some of the important concepts again. Is our data is becoming, we're applying AI not just to images, but to text, to audio, to medical data, to financial data, any kind of data you can think of, we're applying AI, right? So as we broaden the use of AI, one of the things that we really need to understand so that we can have it be as effective as possible is really understand loss functions nicely, because the way the network learns is, so network learns by minimizing the loss function. Okay, so we went through a few of the loss functions. So for example, we talked about MSE, mean squared error loss function, which is basically y minus a square over whatever the number of data, uh, whatever the number of outputs we have, right? For example, if you have 10 classes, then this summation will go from 0 through 9 and y of I minus A of I for all the 10 outputs, right? If there are 100 outputs, it will go through square, right? So same way we can have mean absolute error, where we will apply this yi minus AI and take the absolute value to whatever the number of outputs it is, right? Okay, we also talked about cross entropy as an example. Cross entropy is very useful in multi-class classification. So anytime we have a lot of classes, then cross entropy goes like this, minus y of I log of A of I, right? Sorry, there's a minus sign over here. Either way, okay. I equal to, and again, if there are 10 outputs, you'll go 0 through 9. This is the target value. This is the actual value. And if we try to minimize this, then the network will gradually learn to do a better and better classification, right? So we talked about it if it is a regression type of problem. Like, for example, you are given some stock market data up to a certain time point, and you wanted it to predict the future. Like next day, what will be the price? 2 days later, what will be the price? 3 days later, what will be the price of a stock, right? So here, as you can see, the output is continuous, right? So when we are training the network, we will also give this part as the input, we will have it predict some outputs, and then we'll compare these two to see are they close. If not, we'll go back and adjust the weights. So for regression type of problems, the mean squared error and mean absolute error work typically better. For classification problems, cross entropy works better, okay? But there are many other kinds of problems. For example, in computer vision, sometimes we're interested in recognizing an object, okay? So for example, if there is, let's say, where is the tree or where is the soccer ball, okay, in a given image, okay? So not only we want to recognize there is a soccer ball, we also want to draw a rectangle around it. So then we come up with a box loss, because what if our model says, oh yeah, there's a soccer ball, but the soccer ball is here, okay? So you can see we want it to be very precise, just draw the box. So we can translate this to a box loss so that we can go back and not only have it recognize the category correctly, but also the surrounding box. So what I'm trying to say is loss functions are not just these three. Depending on the type of problem, we will come up with a better and better loss functions, because once again, key thing to remember is the network learns by minimizing the loss function. If your loss function is not the best for your problem, it will our AI model will not do as good of a job, right? So through assignment number 8, I wanted to point out slightly different loss functions. So assignment number 8, we are looking at two types of networks, Siamese and triplet networks. Siamese network, as we discussed, it has two networks. In reality, it's one network, but conceptually, it is two networks. Okay, so what we do is we feed it uh, two different images at the same time. Okay, if the image, let's say this is X1, this is X2. Okay, each one of these, let's pretend it's a CNN network. At the end, as we discussed, before the classification, what will it do? It will produce a latent representation of the input, right? This will also create a latent representation of the input. Okay, so the idea in the Siamese networks was if X1 and X2 belong to same class, then suppose I call this D1, or let me call it embedding 1. Let me call it embedding 2. So E for embedding, which basically means it's a vector. Sometimes we call it also an embedding. Okay. So if E1 is the latent for network 1, E2 is the latent for network 2, meaning as we pass X2. Okay, and they have the same weights and biases. So same W's and B's. If they are convolutional networks, then they have the same kernels as well, right? So the way we want to train this now is, so we will feed both of these to a loss. Okay, so the idea is like this. If X1 and X2 belong to the same class, then distance between E1 and E2 should be less. Okay, because they are belonging to the same category, right? And if X1 and X2 belong to different category, then the distance should be larger. So then increase distance between E1 and E2. So this is how we will train it, okay? So this type of, I put it in plain words over here, but if I translate to a math, that loss is referred to as contrastive loss, because we are contrasting two things over here, whether they are same or whether they are different, right? So if we translate into a math and set this up in our training so that we go and try to minimize the loss, then what will happen is, for example, as I mentioned, for face recognition, this works really well. So if there's a picture of, let's say, we are applying it to face recognition. So let's say there's a picture of Ronaldo, the famous soccer player, and this is another picture of Ronaldo, right? So then what it will do is it will produce a very small Euclidean distance between E1 and E2. Remember, to refresh your memory, how do we compute the distance? So distance, suppose you have 1, 2, 3, 4, 2, 5 is another vector, right? So if this is E1, this is E2 as an example, we refer to the distance as E1 minus E2. And once we do these double bars, this means L2 distance is another term we use, or Euclidean distance is another term we use. Both mean the same thing, okay? How do we calculate it? If E1 is 1, 2, 3, it's very easy. 4 minus 1 square plus 2 minus 2 square plus 5 minus 3 square and square root. So whatever that number is, that's our distance. Okay, Euclidean distance, right? Okay, so if I gave you an example of a 3 by 1 vector, this could be 100 by 1 over here. For example, this could be 100 by 1 over here. It doesn't matter. The distance will still be computed by the first number minus the first number over here square, second number over here, second number over here square, and square root, right? Okay, so how do we define the contrastive loss? How do we translate this simple words that I put in math? So let's go to assignment number 8. Okay, so here's in the very beginning, you'll see this is our contrastive loss over here, okay? Y is our target, and over here, Y will be 1 if they are same class. Sorry, if Y will be 0 if they are same class, opposite. Same class, and Y will be 1 if the two inputs we are giving is different class. And dw is our Euclidean distance. So you can see, so let's take the example of Y is 0. You can see this becomes 0 and this whole term disappears. So you don't have to worry about it, right? Y is 0, so the target is 0. So what does this become? Our loss simply becomes half dw square, which basically means if the two inputs are the same, reduce the distance, because this is how the loss will get reduced if the distance gets reduced, right? So that makes sense, okay? What about we take the opposite case? We are feeding two inputs which belong to different category, right? So then Y will become 1. So then what will happen to this term? 1 minus 1 is 0. So this zeroes out, right? Now we are focusing on second term. So in the second term, Y is 1. So what are we trying to reduce now? We are trying to reduce m minus dw square. Okay, m is a fixed number, for example, 2. Okay, as you can see, the way this will reduce is, let's pretend this varies from 0 to 2. Okay, the distance. Okay, so you can see if it is smaller, then this term will increase. But remember, the goal is to reduce loss, not to increase loss. Okay, so the only way this loss will reduce for the y equal to 1 case is if dw increases. So because as you can see, if it comes close to 2, what will happen? 2 minus 2 is 0, right? But if it is 1, then the loss is increasing. So, so once we put the loss function in this 2 terms together, and we train the network now, then if we tell it, oh, the 2 inputs belong to the same category, it will try to create the latent space so that, so coming back over here. Okay, so then it will create the latent space if the 2 inputs are belonging to the same category, such that this distance is very small. So what is it really doing if I try to visualize this latent representation in this 100-dimensional space, right? So if x1 and x2, remember, as I mentioned, every input is a single point in this high-dimensional space that we are transforming the data to. So in this 100-dimensional space, x1 will be 1 point over here, right? Okay, if x2 belongs to the same category, meaning it's also a picture of Ronaldo, then what will happen? The distance of x2 will be very close to the distance. So x2 will be also over here. So the 2 Ronaldos latent representations, as the network is learning, as it's trying to minimize the contrastive loss, they are appearing very close to each other. So all Ronaldo's picture will cluster like this. Okay. On the other hand, let's say we start feeding it some data where we have Messi. 1 Ronaldo, 1 Messi. So what will happen to x2? In that case, x2 may go somewhere farther away because it's trying to increase the distance, right? If we feed in 2 Messis, then what will happen? It will try to reduce the distance between all the Messis. So as you can see, contrastive loss is transforming the data into clusters in a high-dimensional space so that all these similar categories cluster together. All the categories that are different from each other, we are trying to increase the distance. So once the latent has been learned, and now if we attach a classifier over here, you can see its job will be very easy to create the decision boundary to separate them out into different classes, right? So that is the idea. So if I quickly show you now assignment number 8. Okay, so we'll start out by producing 2 vectors. As you can see, we feed the 2 inputs at the bottom, right? If they belong to the same category, we try to minimize the contrastive loss. This is the latent representation where I say vector A output, vector B output. So both networks have the same parameters, same structure. So when we set it up, there's 2 possibilities to set it up. One is we literally create 2 networks with identical weights and biases in the beginning. The other is, no, just create 1 network. So just create, let me draw it out. Just create this part. Okay. feed in X1, and save the latent. Then what should we do? Feed in X2. Okay, and whatever latent it produces, so suppose we call the previous latent L1. For X2, it will produce latent L2. Now, because we had saved L1, right? Now compute the distance, the contrastive loss, and now backprop through it. And once we have trained it on a lot of similar and dissimilar inputs, then after it is trained and it has adjusted the weights and biases such that for similar categories, the vector it produces is close to the same category, then what we do is at that time, at the very end, we will attach a classifier over here. And now we can use it to distinguish between two categories, okay? So that's how I show you in the assignment. Let me go after. So, and the other interesting thing is from data loaders, data sets point of view, if you take a look at the get loaders function, it has to return now 2 images. Which one is this? Assignment A. Okay. Okay, let me try to. Yeah, so you'll see over here in this line for X1, X2, Y in TQDM train loader, right? So the train loader will be set up so that if X1, X2 belong to the same category, then what should be Y? 0. Okay, if X1, X2 are different class, then it will be 1. Okay, so if you go through how we create the train loader earlier, let me go back to the get loader. Hey, where did I set up the loader? Get loader, normal. No, this is the normal data loader. Okay. Contrast. I'm trying to remember where I put the okay, give me one more second. Let me go back to the beginning. There should be. Oh, right here in the beginning. So you'll see, sorry, not in the loader, but in the data set. So once we create the data set, remember the get items job is to return one training pair, right? But in this case, it will be returning 2 images. And if they belong to the same categories, you'll see int is different. So obviously, if they're same, this will be 0. Otherwise, this will be 1. So the get item in the data set will be set up differently so that it's returning 2 images and 1 or a 0, right? So then we simply set up the network, train it, and if we test it on MNIST data, so like I was saying, there's 2 phases to the training process. First, we just train it for the contrastive loss. There's no classifier. Then after it is trained, we take the part of the network up to the latent layer, and then we attach this classifier. So now we will attach this classifier over here. Okay. And for MNIST, there will be 10 outputs, as you can guess, right? Okay, now we will freeze the weights because it's already trained. It's already learning if it belongs to the same category, then produce this latent vector, which is closer to another image for the same category, right? So how do we freeze weights and biases in PyTorch and only train this part? So PyTorch has a simple property called requires grad. If you set it to false, it will not change the weights and biases of that part of the network. So we will load the already trained the first part of the network. We will already load this that we trained using contrastive loss. And as we load it, once you go through the assignment, you will see that we are adding, so this is where we are loading the torch.load, loading the Siamese network, and then setting the gradient change to false. And then this is the classifier we are attaching to it so that it can categorize it into. So this is typically how we set it up after training, setting it up as a Siamese network, right? So then we can also create a slightly better network, which I briefly talked about in one of the previous lectures, but hopefully you'll understand it better. And by the way, this is the clusters produced if we pick the latent to be 2 dimensions so that we can visualize it. Just 2 numbers in the latent, 2 by 1 as the latent, then we plot the latent. You'll see this is how the clustering it's producing for the different digits. For example, all the 3 digits are this red color over here. Purple is the 4. So these, or it could, this is the 6 as an example, digit 6, right? So it's now as we create a classifier, the classifier can hopefully learn to distinguish the boundaries a little bit better. For example, here, 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 right? So the accuracy hopefully will be better. Okay, same idea we can use for triplet networks, where we set up 3 networks. And we talked about it, X and X plus, our images belong to the same category. And X and X minus are belonging to different category. Okay, and X in this example is called the anchor image in the terminology of the triplet loss. Okay, so for example, this could be the image for digit 2. If it is MNIST, what will be X plus? Could it be 5? No, it will be another 2, right? It has to be the same category. What about X minus? Can it be 2? No, it has to be different category during training. So it could be, for example, 6. Okay, so on the final exam, if I give you this picture and put some images over there, you will let me know, no, this doesn't make any sense, okay? X plus has to be same as X, same category. Not the same image, but same category, okay? So again, they will produce 3 latents over here. Okay, so now my question to you is, as all these are same weights and biases, as we are training it, okay, during the learning process, what it is doing as far as distance between these two is concerned. Is it trying to reduce the distance during learning? Is it trying to increase the distance between these two? Because remember, they are always same category. So it has to reduce. Yes, that's correct. How about this distance? It will try to increase this during the learning process, right? So if you take a look at the loss function, you'll see that's exactly what it's doing. What does these two parallel lines mean? Euclidean distance. Remember I said distance, we indicate one vector minus the second vector, right? See if I gave you, let me go back here. If I gave you some set of numbers, okay, suppose I call it V1. If I gave you another set of numbers, suppose I call you V2, how do I mathematically write the Euclidean distance between V1 and V2? V1 minus V2 double line. This is how we indicate the Euclidean distance. And what's another name for Euclidean distance? L2 norm. Okay. If I'm taking the absolute difference, V1 minus V2 with a single line, this is also called L1 norm. Okay. So anyway, coming back to over here, so you can see our code is basically computing this and computing this. And our loss function will be to try to reduce this part, the distance between these two, and increase this part, right? Okay, so as you go through the assignment, take a look at the code, you'll see exactly how this is being done, right? Okay, so let me give you guys a small break. After the break, I'll talk about assignment number 9. So let me pause for 10 minutes. Okay, so for our overall learning, right? Okay, we looked at some loss functions so far. Okay, for example, mean absolute error, which is the L1 distance, mean squared error, which is the L2 distance, right? We also have looked at so far at cross entropy. And we also have looked at, before the break, 2 losses. What were those? Contrastive loss and the triplet loss. Okay, so if you take a look at majority of these, right? For example, let's take a look at contrastive loss or the triplet loss. What is the key idea in both of these losses? What are they trying to minimize or maximize? Distance between clusters, or distance between similar and dissimilar classes, which is equivalent to, because every class will create a cluster, as you said, distance between clusters. So minimize or maximize distances, right? And as I mentioned, when the number of classes becomes large, okay, then what happens is for multi-class classification, which one of these is the best loss? cross entropy, right? When the number of classes becomes large, cross entropy also does not work well. So it does not. Okay, so it does not work well. It still works, but not as effective as if we have a few dozen or a few hundred classes, right? Okay, so for example, as I mentioned in face recognition, we run into this issue. For example, if you have a security camera at the airport, right? Millions of people are traveling and going through it. So if we would like to recognize, are you the genuine traveler or not? We need like a easily million class problem. And if we had to extend it to all the people in the world, what is it, 6 billion or whatever, 7 billion. So now we're looking at, a billion class network, okay? So we need even a better loss function. Once again, like I keep reminding yourself, the way the network learns is by minimizing the loss function. Okay, if our loss function is very effective, it will learn a lot better, right? So we need even a better, millions of classes are needed. Okay, so bottom line is we need a better multi-class classification loss function. Okay, so in 2019, a very famous paper was written. It's called ARC-LOSS. So I'll give you the idea of the ARC-LOSS and explain, and you'll see fundamentally it's pretty simple concept. Okay, so the simple idea is rather than focusing on distances, maximizing or minimizing distances. Okay, ARC-LOSS's main idea was let's minimize or maximize angle between classes, okay, or clusters, whatever you want to think of it, right? So rather than the distance, focus on the angle, right? See, remember if I give you a vector, right? Let's say if I give you a vector 5, 7 in 2D space, a 2x1 vector, okay, it has a magnitude and it has an angle. Okay, for example, see, that means x is 5, y is 7, right? So x of 5, y of 7, let's pretend it's somewhere over here. Okay, so what is the magnitude? Magnitude is the distance from 0, which is basically 5 minus 0 square plus 7 minus 0 square root is the magnitude. And angle is whatever this angle it creates with respect to the x-axis, right? So every vector, whether it's in two-dimensional space or 100-dimensional space, what I'm trying to say has, so let's say we go to some latent space. So we have a network over here. So it produces some kind of a latent. We feed in some input, whether it's a face or some image over here, right? Okay, so if we examine at the latent, you'll see it will be in some high dimensional space. It will be a vector. So let's say this is our x1. Okay. If now I feed in another image of the same person, so x2 belongs to the same, right? Previously, what were we doing? we were saying the distance will be reduced, this distance, right? This distance, okay? But the problem with the distance is, okay, let's pretend this picture was taken in slightly different conditions, okay? Where the background was different, lighting was different, right? So what may happen is, even though X1 and X2 are the same, depending upon the scenario, see, if I multiply this by 2, a vector by 2, right? It will extend in the same direction. Okay, the magnitude will become bigger. Okay, if it became like this, what happens to the distance now? So if we double the magnitude, the distance increases, okay, or 30% higher magnitude, right? But what about the angle? Angle stays the same. So the idea is, if we are looking at different images that belong to the same category, the inventors of ArcLoss felt that we shouldn't be looking at the magnitude, because magnitude could be affected by, like I said, how the image was taken, even though it belongs to the same category. But if we focus on the angle, then it will be better, right? So let's pick a 2D case, and suppose you have 4 categories of images, right? If we go to the latent, remember, we want to create clustering such that each category is far away from the other category, so the classifier could work better. So suppose here's one category, correct? Where will you create the second category's cluster ideally? Farther away, right? Since there are 4 categories, you might say, oh, let's put the other category over here. You guys agree? And maybe put the other category over here, the third category over here, and another category over here. It will work, right? Okay, what if I have 10 categories? What will happen? Okay, now you will see how many total angles do we have in 2D? 360, right? So that means that every 36-degree angle will be creating the center of a cluster. You get the idea. What if I have 1,000,000 categories? Okay, so you can see, you'll say, oh, this angle technique is not very good, right? So now let me go to the 3D. See if you get the idea first, then I'll show you the math. It's pretty easy, okay? Let's say I have a soccer ball. I can draw a 3D picture. Okay, imagine this is a soccer ball. Okay, on the surface of the soccer ball, I create a category. Okay, then I create another category. Another category, another category. So now imagine on the surface of a soccer ball, can we create a lot of categories as compared to just a circle, right? Okay. So again, let's pretend after creating 20 categories, the soccer ball surface is all full. Everybody is close. Okay. What would you do to make them apart? What will you do to the ball? Increase the size of the ball. Exactly. So that is the idea behind ArcFace. Use a hypersphere. So this ball is in high dimensions, is called a hypersphere. Okay, and make this hypersphere as bigger as you like. And now you can handle millions or billions of classes. Okay, so to give you a tiny bit more background, Okay, how do we go into this angle domain? Okay, so if I give you two vectors, let's say in 3D space, 4, 1, 5, right? Okay, remember once we do the inner product, this is called the inner product. Inner product is basically a corresponding number, multiply and add, right? So what will be the inner product over here? 2 times 4 plus 3 times 1 plus 5 times 1. So 8 plus 3, 11 plus 5, 16 is the inner product, okay? So this inner product, according to math, is magnitude of V1, magnitude of V2, multiplied by the angle between them, okay? So this is a standard physics formula. Anytime you have two vectors, if you do the inner product or the dot product, it's the multiplication of the two magnitudes and the angle between them, okay? How do we find the magnitude of a vector? So what is the magnitude V1? Okay, remember, take the distance from 0. 2 minus 0 square plus 3 minus 0 square plus 5 minus 0 square root. Okay, same way. So can we find this magnitude? Yes. Can we find this magnitude? Yes. Can we do the inner product? Easy. So what is cosine theta? Cosine theta is V1, V2 divided by magnitude of V1, magnitude of V2, right? You guys agree? And so what will be the angle then? Angle will be cosine inverse of V1, V2 divided by the two magnitudes. Okay, this cosine inverse is also called arc cosine. Okay, so arc loss, like I said, will operate on this angle. Now, what if we normalize the vectors, meaning we take this vector V1, we divide it by the magnitude of V1. We take this V2, divide it by the magnitude of V2. Then what will happen to the magnitude of it? It will become 1. Okay, so once we normalize a vector by dividing by its magnitude, then normalizing basically means we're converting its magnitude to 1. Okay, so then if you take a look at the theta between two vectors, what does it become? See, the bottom is 1. So isn't it simply dot product? Take the dot product, take the cosine inverse, will give you the angle, okay? So now let me take you to assignment number 9. Okay, so as I mentioned, the title is Arc Phase Loss for Difficult Multi-Class Classification. Okay, and same thing that we talked about, I gave you a 2D example, how the angle theta is simply cosine inverse of the inner product. And anyway, you guys can go through the example later. And the motivation was, why are we focusing on, I give an example, if you increase the magnitude of this vector over here, the angle stays the same, but the distance becomes bigger. So first, let me give you the idea. Okay, if we take a look at the very end, we do the softmax, right? So let's pretend we have 8 categories. If we do a normal softmax followed by a cross entropy type of loss, then what happens? It will create clusters, right? So in a 2D example, here might be one cluster. This is the center of the cluster. Here's another cluster for another category. This is the center of the cluster, right? But you can see all eventually may have a very less separation between them. Okay. So once we go to the classifier, we'll have a hard time. I mean, it will make some errors in the boundaries, right? So just like we were talking about, what if we pick a hypersphere, make the sphere larger? Then as you can see, what will happen, the clusters will become very compact. I mean, through our loss, we can do that, and we can create a bigger separation between the two. So now once the classifier comes, it will be easy, right? Okay, so if you take a look at the cross, so our typical loss, we take a look at a network, right? Whatever latent it's producing, then we put a classifier over here, and we categorize over here. In the very last layer, what function do we use? Softmax. Remember, softmax is something e raised power something divided by sum over all the e raised power, whatever the outputs are, right? So once we go to a loss function, okay, for a multi-class classification, we use the cross entropy loss. Okay, so if this is our output coming out of over here, this is our output, right? As we go into the loss function. So cross entropy loss, as you know, is what? Minus y of I log of a of I. So, and this is our actual output, right? So if I go over here, substitute this over here. And remember, y of I will be 1 for the category we are recognizing, right? So as you can see, our loss will become I mean, roughly, to get an overall idea, something minus log of e to the something over some e to the something, okay? So sometimes we refer to this as a softmax loss. So some people will talk about it really is not a separate loss. It really, what it means is it's softmax followed by cross entropy loss. So together we refer to it as softmax loss. Okay. Technically, in my opinion, it's wrong to call it softmax loss. The loss is really cross entropy, right? But what I'm trying to say is this formula effectively, if I substitute the output, becomes like this. Okay. Now, if this was a Siamese or triplet type of network, right? Remember, over here, it is really trying to focus on distances. Okay. So in the, if we go back now, okay, so if you take a look over here, okay, so suppose, okay, we have some network. We have some latent or some latent space over here, right? Okay, our classifier is simply a two-layer network, right? So what does that mean? It is essentially two weight matrices over here, okay? Just for easy understanding, let's put one weight matrix over here, okay? Suppose I call this L1, the latent, right? Okay, so as we go to the output of the classifier, okay, how is output related to, let's pretend there's a single weight matrix where you have just one set of neurons over here. Then how is output related to it? Okay, because this will be L1 by 1, right? So you can see this one, and suppose the output over here is, let's say, C. C is the number of classes. Okay, so then this weight matrix should be, or let me just call it L rather than L1. So this is L by 1. So this should be, or C by L, either way, right? So you can see, or L by C. All right, let's make it L by C. Okay. Then, as you can see, it should be W transpose times. If this is out, the dimensionality, or let me just call it latent. So times latent, right? So latent is L by 1. This is C by L, C by L. So then you can see output will be C by 1, okay? So if we treat this now as having some vector with some angle, let's say theta 1. So this is our latent, okay? As we pass it through a weight matrix, what will we get? We'll get C. Okay, you can think of conceptually C that we are getting over here is as if it's doing a rotation on the latent. So whenever we multiply by a weight matrix, essentially it's rotating whatever the input vector is. In this case, it's latent. Because like I said, in the arc loss phase, we're focusing on the angles, not the magnitude, right? So whatever C is, it will have an angle, right? And the angle it produces obviously depends on the weights, because those are the ones that are being multiplied to the input, okay? Or let me give you another view over here. Another view would be, okay, let's pick an example. Let's say latent is 100 by 1. Okay, let's say this is 10 by 1 is our C, the final output, right? Okay, so now W will be 100 by 10. Okay, so what does that mean? There are 100 rows and 10 columns, right? So 10 columns. So if you take a look at W, right? Let me call this W1, W2, and W10, right? Okay. Each one of these is a vector, right? Okay, so take a look over here. If I multiply, let's say, L by W1, okay? I do the inner product. So as we discussed, the inner product between two vectors is what? Magnitude of L, magnitude of W1 times cosine theta, right? So if both are unit vectors. Then as we are multiplying this latent, right, isn't it creating the cosine of the angle between the two vectors, right? So you can view this as each output, the 10 categories that it's producing, each one is being rotated depending upon this W. So in the learning process, so what I'm trying to say is we started out with some data. Let's say this is the angle at this point over here. This is the angle, right? As we pass through this W transformation, what it's doing is, depending upon the category, which category it belongs to, it will rotate one category, maybe one category will go over here, another category will go over here, another category will go over here, right? So if we can, in our loss function, force this distance to be, or this angle to be higher, it will do a better job. So coming back to the loss function, okay, the loss function for the arc loss function, let me go over here, is over here. Okay, so this is our loss function, right? Okay, so this S over here is our scaling factor. So this makes the hypersphere as big as we want, okay? So if you pick S to be 10, it will be a bigger sphere. S to be 100, it will be even a bigger sphere, right? And if you take a look at cosine of theta of yi is the angle it will produce for one category. Yi is one of the categories, right? Okay, and plus m, what are we doing? For example, over here, let's say it produces this angle, right? Plus m, we are saying, okay, move it further. Not only what we learned, but we are pushing it even further over here, farther away. Okay, and where's this minus coming from? Cross entropy. Where's this log coming from? Cross entropy loss, right? So if this was a normal loss function, right, coming back over here, what I'm trying to say is, okay, if we were not focusing on the loss function, then the output over here is W transpose times latent, right? The normal loss, which is softmax plus cross entropy, if I write that equation, what will that look like? That will look like minus log, right? And over here, you will see e to the W2L over something summation e to the WTL. And of course, I can put L of I depending upon which category it is, and then do the summation over here. So normally we are focusing, what I'm trying to say is on the magnitude aspect of the vectors. So arc loss people said, no, as we do W2Li, make this unit. And like I said, as we do, right, and replace it by the cosine of the angle, and then further add plus m to it so that we can move it farther away from each other. So that is the general idea of the arc loss loss function. Okay, so try to go through it, see if it is making sense, and I'll just show you the final pictures, and you'll see by looking at the final picture, see if it makes sense now. If we again go to the 2D latent space, do you see it as creating angles between classes? and it's pushing them farther away. So you can pick S to be bigger and it will move out, right? So that is the arc loss function for especially for high number of classes. This is proven to be a very, very good loss function, right? So anyway, I will last 1 minute I'll show you is if you search for this paper, right? It was called arc phase loss. Let me see. Yeah, this is the one. So this is the arc phase. You can see 7,000 citations. So it's a very, very famous paper. And if I quickly show you their picture. Okay, so if you take a look at this picture, you'll see this is the latent being produced. Okay, then what they do is they multiply it with one more matrix over here so that they can create the rotations. Just like I was saying, if we multiply by W, then it will rotate this for, and the size of the W will be the whatever this latent dimension is times the number of categories, the number of classes, so that each class is learning to rotate a little bit differently, so that it can place it on the hypersphere, right? In this margin, M margin, you'll see, let me see if I can make this picture bigger. Okay, so you'll see this is the normal angle for the ith class, and then M will further push it away. Okay, so that is the general idea. Anyway, so that will give you good understanding of the different loss functions. How do we come up with something new, right? Okay, now I know some of you are interested in pursuing it further during the holidays. Let me give you an idea. You can work on it and stop by to talk to me if you're more interested. So okay, so we, for example, assignment 8 and 9, we looked at Siamese and triplet networks, right? So remember, we often use the term Siamese twins. If there are two people who look identical, right? So there's another famous paper by Jan LeCun and his team. It's called Barlow twins. Okay, you'll see again more than 2,000 citations. And it is an interesting idea. So if I show you the architecture, you'll be able to understand it. Okay. So because it's twins, right? You'll see there are two networks being used. Okay. So they have like a network over here, and this is called an autoencoder. To give you a quick idea of an autoencoder, in an autoencoder, what we do is, let's say you have a 100 by 100 image, just to give you a simple idea. Okay, we can create CNN-based autoencoder or a linear layer, right? So if I linearize it, you'll see this will be 10,000 by 1 numbers, right? So if I pass it through, let's say, 500 neurons, Then I reduce it to, let's say, 100 neurons. Then I reduce it to, let's say, 50 neurons. So you can see what I'm doing is I'm gradually compressing this data, right? Then I start increasing it back to 100 and back to 10,000. Okay, so you can see. Okay, so if I feed in 10,000 numbers, I will get 10,000 outputs. And I can use a mean squared error loss over here. So this is called unsupervised learning. So during training, all I have to do is feed in the same image. So if it's the image of a tree, it will learn to reproduce image of the tree. So what is it learning? It's learning to compress the data, then decompress it. Okay. After it has been trained on many, many images, so we're not worrying about the category it belongs to. We are just making it learn what is a good latent representation of different images. Once it has been trained, what we'll do is, so this part we refer to as the encoder. This part we refer to as the decoder. So once it's trained, we remove this. Into this part, we will attach a classifier. And then we can classify whatever category we wanted it to be used for. Because now it has already learned what are the important features that represent a particular image nicely, right? Okay, so if we take a look at Barlow Twins paper, okay, so this is an autoencoder over here. We compress, decompress. We have an autoencoder here, compress, decompress, right? We feed in one image. In their example, if you take a look, what we did is we added a noise, slight noise. We distorted this image. So this is the same image undistorted. This is distorted, okay? Then we have it compress and decompress, compress and decompress. So both of these will be now similar to X, okay? Then we create a loss function over here, which is basically learning the correlation between these two. So if we have a diagonal identity correlation, then basically it's learning a very good latent representation of it. Once it has learned, we can remove everything. And now we can attach a classifier over here, and it will do supposedly a better job, okay? So the question is, we already have an idea of how Siamese and triplet networks work. Okay, will they, so think about it, will they benefit from further the Barlow twins idea? Okay, meaning we're trying to create a better face recognition system. Can we combine Barlow twins and a triplet further with an arc loss function? Like a very accurate face recognition system. Read the paper, stop by, I'll give you further more ideas on it. But anyway, as you go through and prepare for the exam, remember the goal of the exam is, think of it like it gives you an excuse to review and solidify your own concepts. I don't believe in exams that much. It doesn't indicate anybody's capability, but treat it another opportunity to learn. Hopefully after this course, you have, if even if some of the concepts were not as clear during the holidays, go back and review it again. We all learn a lot better when we do it second time and third time. But if you have a very good foundation, then you can do advanced things and they will become a lot easier because your foundation is so good, right? Okay, so keep learning. And last thing I will do is I'll take a snapshot of whoever attended today. So that tells me how serious you are about the course. I'll give you anybody attending today till the end will get a higher grade. Anybody who was absent, I will reduce their their grade. So, but anyway, try to work hard. So